Welcome to all students in lecture 11. In last lecture, we will discuss the hybridization of the D2sp3 complexes. It means that the d orbital, inner d orbital is used in that hybridization. It's called as the inner orbital complexes, and the outer orbital is involved in the hybridization. It's called as the outer orbital complexes. See here in this example, today's lecture 11. The outer orbital complexes involving sp3d2 hybridization. It is called as the high spin complexes. Why it is called as, first of all, we will see what is meant by high spin complexes and what is meant by low spin complexes. High spin complexes means the magnetic moment of the complexes is not decreased or the same as that of the free ions. If the magnetic moment of the free ion is 5.90 bm, then in a complexes also the magnetic moment is the same, that is the 5.90 bm. It is called as the high spin complexes. In low spin complexes, the magnetic moment is decreased from the free metals ions. Hence it is called as the low spin complexes. These are the examples are the high spin complexes involving the sp3d2 hybridization. sp3d2 hybridization, because d orbital is used, is the outer side d orbital is used. The first example here, explain the formation of chromium H2O6 dipositive complexes. In exam, question may be asked, explain the formation of Cr H2O6 dipositive complex. So how to write the answer? The answer in this way. Answer: the central metal atom of this complex is a chromium. The central metal atom of this complex is a chromium. Then coordination number of the central metal atom, that is the chromium. Coordination number means how many H2O atoms is attached to the chromium. Total number of 6 H2O atoms is attached to the chromium. Hence, coordination number of the chromium is a 6. The next point is oxidation state of chromium. Oxidation state of chromium, the charge present on the complex line, that is this 2 positive. This is called as the oxidation state of the chromium. Then oxidation state of the chromium is dipositive or 2 positive. Then write down the atomic number of chromium. Atomic number, what is the atomic number of the chromium? Is the 24 atomic number. Then write down ground state electronic configuration of chromium, or electronic configuration of chromium in the ground state. In ground state, chromium shows the exceptional electronic configuration, that is the Ar3d54s1. This is the exceptional electronic configuration of the chromium, that is the 3d54s1, because 6 electron is present in a valence orbital, or the valence orbital, or the valency of the chromium is a 3d6. Hence, Ar3d54s1 is the ground state electronic configuration of the chromium. Then excited state electronic configuration of the chromium is present in a dipositive oxidation state. Hence, it donates the 2 electrons to the hence it acquires the dipositive oxidation state. From this ground state, if 2 electron is removing, 1 electron is removed from 4s orbital and another electron is removed from the 3d orbital. Then there is formation of the Ar3d4s0. All this information of the hybridization is written in a square bracket or the box diagram. 3d, 4s, 4p and 4d orbital. Then ground state electron configuration of chromium is 3d54s1. This is the 1, 2, 3, 4, 5 according to the Hans rule. 1 electron is present in a s orbital. Then 4p and 4d orbital is a vacant. Then electronic configuration in a excited state. In excited state, 2 electron is removed because oxidation state of the chromium is a +2. Hence, 1 electron from the 4s orbital, 1 electron from this d orbital. This electron is removed and this electron is removed. Then excited state of Cr dipositive is 1, 2, 3, 4. This orbital is vacant, this orbital is vacant, and all the other orbital 4p and the 4d orbital is also vacant. Electronic configuration in CrH2 6 diapositive complexes. See here what happens when 6H2 molecule or 6H2 molecules is come close towards the chromium or the centimeter atoms or the bonding formation. That time lone pair of electron of H2O having the two lone pair of electron. Then one lone pair of electrons he donate in a vacant orbital. Hence, H2 cannot donate one d orbital. He donate one of H2 molecules, donate 2 electrons. Second, donate 2 electrons, 2 electrons, 2 electron pair, 1 electron pair, 1 electron pair. In this way, they are donate the electron pair in a central metal atoms. And see here, 4s orbital, 1s orbital, 3p orbital, 1, 2, 3, 1, 2, 3, 3p orbital, p3, and outer orbital. See here, 4d orbital. 4d orbital is involved in the hybridization. 4d orbital. D2 orbitals is involved, or 4d 2 orbitals is involved. sp3 d2. D2 means 2 orbital of 4d orbital is used in the hybridization. When such hybridization acquires the sp3 d2 hybridization, or this molecule acquires the sp3 d2 hybridization, and molecules geometry of the complex is the octahedral, or geometry of the complex is the octahedral in nature. Here sp3 hybridization is called as the outer orbital complexes. Why it is called as the outer orbital complexes? Because outer 2d orbital is involved in the hybridization. Hence it is called as the outer orbital complexes or outer orbital complexes. The magnetic moment of these complexes is a paramagnetic nature, because 4 electrons is present in an unpaired electron, or 4 unpaired electron present. See here, 1, 2, 3, 4. 4 unpaired electron is present, and H2 molecules cannot pair up or force the electrons to pair up, because it is a weak ligand. Hence, it cannot pair up the electrons. Hence, this complex shows the paramagnetic nature, and magnetic moment of the complex is a 4.90 or 4.90 Bm. This complex is called as the high spin complexes because the magnetic moment of the free metal ions is also 4.90 Bm, and in complexes also it shows the 4.90 Bm. Hence, this complex is called as the high spin complexes or the high spin complexes. Then lastly, the structure of this complex or structure of this complex is a octahedral in nature. I draw the diagram here. Octahedral complexes or the structure of these complexes. Geometry is octahedral. The structure of complexes, see here. Chromium, H2O, 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 chromium H2 diapositive. Structure of CrH2 in this way, this is the structure of octahedral molecules CrH2 diapositive complexes. In this way, we have to write in exam in this manner or in this fashion, so we get the out of marks. Then second example I take here. So the second example of the complex is of outer orbital complexes is Fe F6 triangle complex. Same question is asked, explain the formation of Fe-F6 triangulative complexes. The answer of this question is right in this manner. Name of central metal atom or the central metal atom CMI of this complex is ferrous. Then oxidation state of Fe is equal to 6 minus 3 is plus 3 or plus 3 oxidation state. Then write 6 coordination number of this complex is 6 because 6 fluorine is attached to the Fe or the sentimental atoms. Then atomic number of Fe, atomic number of Fe, what is the atomic number? 26. 26 is the atomic number. Then write down ground state electronic configuration of Fe. AR 3d6 4s2. AR 3d6 4s2 is the ground state electronic configuration of Fe because 8 electron is valence or 8 valence electron is present in a Fe. Then in excited state, oxidation state of Fe is a plus 3. Hence, this complex in excited state donate the 3 electrons. Hence, in excited state electronic configuration of Fe tripositive. 2 electrons is removed from this and one of the electron is removed from the 3d orbital. Then electronic configuration is 3ar 3d5 4s0. This information is written in a box diagram here. Ground state electronic configuration is equal to 5d orbital here, 3d, then 4s orbital, then 4p orbital, and lastly is the 4d orbital. 3d, 4s, 4p, and this is the 4d orbital. In ground state, electron configuration 3d6. With the help of the Hertz rule, we write here 1, 2, 3, 4, 5, 6, 6, then 4s 2, then 4p orbital and 4d orbital is a pattern. In excited state electronic configuration is equal to, in excited state what happens? Tripositive is oxidation state or 3 electrons is donated, then random 4. One of the s electron, 2 electrons is donated from the 4s orbital and 1 electron is donated from the 3d orbital. Hence, in excited state 1, 2, 3, 4 and 5, this orbital is vacant. Then electronic configuration in complex Fe, F6 tri-negative is equal to, see here, electron not pair up. Why it is not pair up? Because fluorine is a weak field ligand. If fluorine is a weak field ligand, hence it cannot have the power to force up the electrons or pair up the electrons. Hence there is no any vacant orbital in a 3d orbital. For this hybridization, the electrons coming from or the electrons donated by the fluorine ligands, they donate the electron in a 4s 4p. See here, 5, 1, 2, 3, 4 and 5. Then 4s, this is the 4p and this is the 4d. The 6 fluorine ligands donate the electrons to the vacant d orbital of the ferrous for the bonding formation. So one of the fluorine, second, third, fourth, fifth and sixth Fluorine cannot donate this electron because the coordination number of the fluorine is Fe is a 6. Hence 6 fluorine ligands donate lone pair of electrons in a vacant orbital in this way with their cross sign. I will show you. See here what happened. 6 fluorine ligands donate the lone pair of electrons in a vacant orbital of the 4p and the 2 vacant orbital of the 4d. And this 4d is the outer orbital complex. This is the outer, not the inner. When 1s orbital is involved in the hybridization, p3, 1, 2, 3, p3 hybrid orbital is involved in the hybridization, and 2d, 1, 2, 2d orbital is involved in the hybridization, then molecules having sp3d2 hybridization. Molecules having sp3d2 hybridization, and if the molecule of the hybridization is sp3d2, then it acquired the octahedral geometry. It acquired the octahedral geometry. Octahedral geometry, and these complexes, or in these complexes, outer d orbital is involved, or 4d orbital is involved in the hybridization. Hence, it is called as the outer orbital complexes. It is called as the outer orbital complex. It is called as the outer orbital complexes. And the magnetic moment of the, see here, total number of 5 unpaired electrons present in these complexes. Hence, it is called as the paramagnetic nature. Paramagnetic nature. Paramagnetic nature. The magnetic moment of these complexes is 1, 2, 3, 4, 5. If the 5 unpaired electrons, the magnetic moment is 5.92 BM. And this complexes is called as the high spin complexes. This complexes is called as the high spin complexes. Why it is called as the high spin complexes? Because magnetic moment of the free ion is also 5.92 BM. And in complexes also it shows the 5.92 BM. Hence this complex is called as the high spin complexes. It means that Fe-F6 triangulative complexes shows the octahedral geometry. Hybridization is sp3d2. This complex is called as the outer orbital complexes because outer d orbital is involved in the hybridization, and the paramagnetic nature because it consists of the 5 unpaired electrons, and it shows the 5.92 BM magnetic moment. And this complex is called as the high spin complexes. Then lastly, the structure of the complexes. This is the all described here. Then lastly, draw the structure of these complexes. How to draw the structure? Octahedral geometry. See here. This is on the plane and above the plane Fe, then fluorine ligand 6, fluorine, and triangulative complex. This is the structure of the Fe-F6 triangulative complexes. This is the example of the sp3d2 hybridization. sp3d2 hybridization. This is the second example. See here the next tetrahedral complexes with sp3 hybridization, or all the examples of the sp3 hybridization having the coordination number 4. The geometry of the complexes is a tetrahedral geometry. The question may be asked in examination. Explain the formation of Mn-Br4 dinegative complexes. In these complexes, Mn-Br4, the coordination number of the complex is 4. If the coordination number of the complex is 4, then there is possibility of the 2 hybridization. The first is a sp3 hybridization, and the second possibility is that the dsp2 hybridization. So this is the example of the sp3 hybridization. See here how to write the answer of this question. Firstly, write down the central metal atoms of this complex is Mn, Then coordination number of the complex is a 4. Coordination number 4. Why? Because 4 bromine atoms is attached to the Mn molecules. Then oxidation state of this complex or central atom is 2 positive or dipositive. Then atomic number of the manganese is 25 atomic number. Then ground state electron configuration of the Mn is Ar 3d5 4s2 because 7 valence electron present in a Mn. Then write down the excited state electronic configuration. In excited electronic configuration, the oxidation state is +2, hence it remove the 2 electrons or it donate the 2 electrons. Then one of the 2 electrons from the 4s orbital is donated and the excited state electronic configuration of this complex is Ar 3d5 4s0 because 2 electron is donated. This information is written in a box diagram. Ground state electronic configuration of the chromium 3d5 4s2. Then according to the Hund's rule, 1 2 3 4 5 4s2 for 2 electron or electron pair is present in a 4s orbital. In excited state electronic configuration, 2 electron, these 4s2 electron or outer electrons is removed, hence 4s0 here, and 3d orbital 1 2 3 4 5 electrons is present in a 3d orbital. In sp3 or in a 4 or tetrahedral complexes, there is no effect or bromine is a weak field ligand. Hence, this bromine or this ligand not power to pair of the electrons in a 3 orbital. Hence, this 5 electrons is present as a unpaired electron. And next, electronic configuration in complex, that is Mn Br4 dinegative complex. See here how the hybridization is occurred. 4 5, then 4s and 4p atomic orbital. This 5 electron is unpaired as it is. The 4 bromine atoms, one ligand, second bromine ligand, third bromine ligand, and fourth bromine ligand come close towards the bonding formation and we donate the lone pair of electrons to the Mn vacant orbital. The first donate, second, third, and fourth. I see here cross side electron pair donated by the bromine atoms. In this, see here what happened when one s orbital, this is the s orbital, when one s orbital, then p orbital, how many? 1 2 3, 1 2 3. When one s orbital and 3 p orbital combined together, then there is formation of the sp3 geometry or sp3 hybridization. If the complex is having the sp3 hybridization, then it acquired the tetrahedral geometry. And if the complex is a tetrahedral geometry, then what is the magnetic moment? It consists of the 5 unpaired electrons. Hence, the magnetic moment of this complex is a paramagnetic in nature. And magnetic moment of the complex is a magnetic moment is equal to 5.92 bm. And lastly, the structure of the complexes is, it is a tetrahedral complexes, hence the structure of the complexes is, see here, this is the bromine Mn Br, one of the Br atoms, and here is the Br atoms. Join all these and right here the 2 negative charge. This is the structure of these complexes. It is called as the tetrahedral geometry. In this way, we can explain all the details or all the information of Mn Br4 dinegative complexes or Mn Br4 dinegative complexes. In this way, this is called as the complexes with the sp3 hybridization and paramagnetic nature, magnetic moment. See here the last example of the square planar complexes with the dsp2 hybridization. If the complex is having the partition number 4, then its possibility of the 2 hybridization. One is the sp3 and second one is the dsp2. if the complexes acquires the sp3 hybridization, then it shows the tetrahedral geometry, and if the complexes show the or acquire the dsp2 hybridization, then the geometry of the complexes is a square planar complexes or the square planar complexes. Square planar geometry is acquired. See here, the one of the example is explain the formation of NiCN for negative complexes. NiCN4. How to write the answer? In answer, write central metal atoms. Name of the central metal atom is nickel. Then quadration number of nickel is 4. See here, quadration number is 4 because 4 CN atoms or 4 ligands, 4 CN cyanide ligand or cyanoligand is attached to the nickel atoms. Then oxidation state of Ni is 2 positive, and atomic number of the complexes is, or atomic number of the Ni is 28. Then similar as we see, the ground state or electronic configuration or ground state electronic configuration of Ni is equal to Ar 3d and 4s. 3d, total number of 10 valence electron present in a nickel, then 3d 10 4s 2. This is the ground state electronic configuration of the 3d 8 4s 2, total number of the 10 electron present in a valence orbital. 3d 8 4s 2 is the ground state electronic configuration of the nickel. Then in excited state, the 2 electron is removed because oxidation state of nickel is a 2. Then it removes the 2 electrons. Then excited state electronic configuration is equal to Ar 3d 8 4s 0. 3d 8 4s 0. See here in a box diagram, ground state electronic configuration is equal to Ni. This is first d orbital, 1 2 3 4 5, 3d orbital, 4s and 4p atomic orbital, 4p atomic orbital. This is the 4p atomic orbital. See here, 3d8 according to the Hertz rule, write down 1 2 3 4 5 6 7 8, 3d8 4s2 1 2. In excited state, what happened? 2 electrons is removed from the 4s orbital. Hence, this 2 electron is removed in a excited state. Hence, excited state electronic configuration is excited state electronic configuration of Ni dipositive is equal to, write down in a bracket 1 2 3 4 5. Then next orbital is 4s and 4p. Only 1 2 3 4 5 6 7 8 electron is present in a 3d orbital, and 4s orbital is a vacant. See here what happened here in excited state when 4 CN ligand is come close towards the nickel for the bonding formation, then CN is a strong field ligand. Hence it pair up the electron. And electron pairing is take place in a 3d orbital. Hence these 2 electron is pair up, and one of the electron is from this place to the excited or pairing with these electrons. Hence one of the orbital is vacant for the bonding formation. Because in excited state these 2 electron is a pair up, and in hybridization state, see here what happens. In hybridization state electronic configuration of nickel Cn4 dinegative complexes 1, 2, 3, 4, 5. This is the 4s and this is the 4p atomic orbital. The pairing of electrons take place in this way. All the electrons is paired up. One of the d orbital is vacant here for the bonding formation, and 4 Cn ligands, 1 Cn, second, 3 and 4 Cn ligands come close together for the bonding formation and donate the electron pair in this way. Donate electron pair in this way. 4 Cn ligand donate the electron pair in a vacant orbital of one of the d orbital, one of s orbital, and two of the p orbital. Because coordination number of the complex is 4, hence the only 4 Cl ligand is donate the electron pair in this manner or in this fashion. When one d orbital, see here what happened, one d orbital, this is the one of the d orbital, one s orbital, this is the d, yes. And how many p orbital? The two p orbital combined together, they form the hybridization or the hybridization state. Shows the geometry is the D.Sp2. Hence, this complex requires the D.Sp2 geometry, that is the D.Sp2 hybridization. And if the complex is having the D.Sp2 hybridization, it acquires the square planar geometry. Then it acquires the square planar geometry. Hence, this complex shows the square planar geometry, and these complexes does not involve any unpaired electron, or this complexes shows no any unpaired electrons. Hence, this complex is a diamagnetic in nature. Diamagnetic in nature, and the magnetic moment is a 0, or it does not show the magnetic moment. And lastly, the structure of the complexes is the square plane complexes show this type of structure, that is the square planar in simple mid-atom Cn, 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 Cn. This is the square planar geometry, di-negative. This is the structure of Ni Cn4 di-negative complex. Square planar structure, it means that this complex shows the D.Sp2 hybridization. Geometry of the complex is the square planar geometry, and magnetic moment, the magnetic moment or magnetic nature is a diamagnetic, and the magnetic moment is 0, and the structure of complex is a square planar structure. In this way, we have to write the answer in an examination. This is the last example of the D.Sp2 hybridization.